Also, sir, in the previous example, example
Yeah,
2, you
yeah.
wrote down, 2 by s minus 1, and
Yeah.
then you drew the loop, and then you took the loop transfer function as 2 by s minus 1. Should it not be like something like, gs by 1 plus gs? Like, you, okay, so like, I'm like confused about a notation here. So are you saying that, this is the total gs by 1 plus gs, or here?
This
Or
loop transfer function GS into CS.
okay.
LS is so gain margin, phase margin, any gain margin, phase margin, all these things, root locus, all these things are drawn for the loop transfer function. Okay, so loop transfer function is planned into plan transfer function into controller transfer function. Got it?
Yes, sir.
Sir, so sir, I have a doubt. Like, so in the loop transfer function, so if there is a return gain, so that will also be included in LS.
Yeah, all the things I have considered inside LS. There is no other gain. Okay,
Okay, sir.
that
Thank
this
you.
is the diagram that I have drawn. Okay, suppose LS is suppose 3 divided by S minus 0.5 into S plus 2 whole square. So if you here nominal gain suppose here K, nominal gain K, so K equal to 1, K equal to 1, that is nominal gain 1, nominal gain 1. So for determining gain margin, what I will do, I can increase K from 1 to K max. So that K max will give you upper side gain margin, and I can reduce K from 1 to K mean, and that K mean will give you lower side gain margin. Okay, so this is the loop transfer function, suppose. So now I will draw the root locus for this. My shape is not important, but the imaginary axis crossing and all these things are important. So suppose here one root is at, so here one root is at 0.5 and another two roots are at minus 2, minus 2. So how the root locus will look like then? Root locus, if you draw it, root locus will look like this. So three roots will go to infinity. So root locus will go like this. Okay. So this is your k equal to 0. So this is your k equal to 0, and here k equal to infinity, and here k equal to infinity, here k equal to infinity. So if you check, then this one, this point here k, here k will be equal to 2 by 3, and here k, here or here, whatever it is, here k is equal to 3. Okay, so then from the root locus it is clear that k can be reduced up to 2 by 3 and can be increased up to 3 till the system, closed loop system, remains stable. Okay, so the upper side gain margin, upper side GM, lower side GM, lower side GM equal to 2 by 3. Okay, so the same thing. So in this way, using root locus, you can determine upper side gain margin, lower side gain margin. Similarly, you can also use Nyquist plot for this. Just for the same example, I will draw Nyquist plot and I will say how to determine this lower side gain margin and upper side gain margin. This for this system, the Nyquist plot will be like this. So using Nyquist plot, so the Nyquist plot you can also do. So this is real of Lj omega, and this side is imaginary of Lj omega. And if you draw Nyquist plot for this plan, for this loop means again and again I am telling loop means controller into plant. Controller into plant, into actuator, sensor, all the gains in cascade. That is loop transfer, GS into CS, because actuator we normally consider, actuator and sensor dynamics we normally consider inside the plant. So GS, the controller is CS. So loop transfer function LS is GS into CS or CS into GS. That is for CISO system, GS into CS equal to CS into GS. It doesn't matter. So the the Nyquist plot for this plant for this LS will be like this if you draw it. And please check it. I'm just drawing. So please mute yourself if you do not have any question. So here omega equal to 0. Yes. So here omega equal to infinity. Here omega equal to minus infinity, plus infinity. Okay, plus infinity I have not written. This is omega equal to 0 minus. Okay, and this point. So suppose what is this point? This point will be minus 2 by 3. This point will be this point. This point will be minus 2 by 3, and this point will be minus 3. Sorry, it will be not 2 by 3. This is 3 by 2. Sorry. This should be 3 by 2. This should be 1 by 3. Sorry, this should be 1 by 3, because ultimately then your yeah, this should be 1 by 3. 1 by 3, and this should be, that means this point, and this point is minus 3 by 2. So that means what is your, so suppose this is your A1 and this is your A2. What is your lower side gain margin? Upper side gain margin? GM equal to 1 by A1.
Okay.
1 by A1. This is very crucial. Gain margin, phase margin is not so easy thing. So if using Nyquist plot, Bode plot, even lower side gain margin, upper side gain margin, you will not get in book. They in book they have only considered upper side gain margin. Lower side gain margin you will not get. So only in journals you will get, so in some journals papers. So this is 1 by A1. So 1 by A1 means 3. So lower side gain margin, lower side GM equal to 1 by A2. So that is will be equal to 2/3. So in this way you can use. So one important thing is that the phase margin is always so since the Nyquist plot or Nyquist plot is always symmetric with respect to x and y axis. So gain margin, lower side gain margin, upper side gain margin exists, but plus minus phase that has to be inserted into the loop so that the system, closed loop system, will become unstable. So that will remain same. That means there is no term like upper side phase margin, lower side phase margin. So that is plus b, because this is not there because the Nyquist plot is symmetric with respect to x and y axis. Okay. So that's why that comment I am just writing. Note, Nyquist plot is symmetric with respect to x and y axis. Therefore, there is no term like positive phase margin, negative phase margin. Thus, okay, positive phase margin, negative phase margin, that kind of term is not there. So here for the above example, for example, what is the phase margin? How to okay? So I should write this one. That is minus 1 point. Minus 1 point will be inside. So how to determine phase margin? For obtaining phase margin, we'll do we'll draw a unit circle. Okay. So with radius minus 1. So this is unit circle. So what is your phase margin? So this is your phase crossover frequency. So gain crossover frequency. So the gain crossover frequency is this one, and what is your phase margin? Either this one, upper side or lower side phase margin, as I said, it is same. That you can also see from this figure. So what is your phase margin? This phi. This phi is your, so phi is your phase margin. This is an important document actually regarding gain margin. So I think now it is clear to you how to determine gain margin from root locus. It is very important information. I think it was not taught earlier. Determine phase margin you cannot determine using root locus, but gain margin, particularly gain for both upper side lower side gain margin calculation, root locus is a very effective tool. Nyquist plot is a general tool, so you can always use to determine all the things as I have shown in this figure. Okay, so now slowly I will move. So now what is the just limitation of, just I want to say what is the limitations of GMPM. What is the limitation? So their GMPM can guarantee robustness against pure gain variation and phase variation. Okay, pure. So this term is important. Pure. So this is the limitation. Pure gain variation and phase variation. That means this is called gain phase tester. Let's do it. Or pure gain variation, phase variation. So for example, so that's why this is called gain phase tester. Gain phase tester is what? You will add this kind of variable into the loop e to the power minus j5. Okay, so this is your gain and phi is your phase. So that's why gain phase tester. So simultaneously, so when you will determine gain margin, at the time you will set phi equal to 0, and when you will determine phase margin, at the time you will set k equal to 1. This is gain phase tester. So now, so this is the limitation of gain margin, phase margin, or classical margin. Now I will try to say how this can be. Means what are the advanced robustness measures which can tackle this means general planned variations, maybe zero variations, maybe other parameter variations. Okay, how in general those means in in modern control those kind of things are tackled. So now we'll discuss robustness.
Sir,
Yes.
sir, if we can guarantee robustness, then how can it be a limitation?
No, here that is the limitation. Now only pure gain variation. Robustness against only pure gain variation or pure phase variation. If there is any other parameter variation other than gain and phase, okay. Suppose pole variation or zero variation.
Okay, okay.
Got my point? So robustness against parameter variation. So now, so sensitivity. I do not know whether sensitivity term has been taught. Sensitivity, loop sensitivity, closed loop sensitivity, all these things have been taught or not. Anyway, whatever things are needed here that I will discuss in brief. So this is your suppose planned G S comma alpha. So alpha here is an uncertain parameter. So controller is fixed. Controller, we normally do not consider uncertainties in the controller because nowadays these controllers are implemented digitally. So there will be very little amount of inaccuracies. So in fact, no inaccuracies nowadays. High-speed digital controller, digital processors are there. So we can assume that the controller is fixed. But so this is suppose R reference input. This is suppose output. So alpha is uncertain parameter. So it is not necessary gain or any. So it can be any pole variation. It can be any alpha. Can be any pole. Can be zero. Can be any other parameter. So now, so one term sensitivity. So sensitivity term I will bring S alpha G. S alpha G. This is this I will term sensitivity of G with respect to alpha. That means sensitivity of G when alpha is varying. This I will define like this: limit del alpha tends to 0. Okay, del G by G divided by del alpha by alpha. Okay, so this you can also write like this, equal to del G by G divided by del alpha, sorry, delta alpha by alpha. Okay. So del G by G divided by delta alpha by alpha. So now this is your sensitivity. Similarly, so now this is equal to, here you can see open loop sensitivity, because here if there is no controller, so this is the sensitivity of G with respect to alpha. This is open loop sensitivity. Okay, this is open loop sensitivity. Now what is closed loop sensitivity? S alpha t. Here t is the input output transfer function, t is gc by 1 upon gc. So this is equal to sensitivity of t with respect to alpha. That means as your alpha changes, so what is the sensitivity of the closed loop transfer function t with respect to alpha? That is called, that we are denoting as S alpha t. So what is t? T I am writing, so t equal to gc by 1 upon 1 plus gc. So this is equal to, again using the same notation, same definition, del t by t divided by del alpha by alpha. So these things has been taught in class. Hello?
I don't think so. The sensitivity is not taught. Some other
Not
measure
taught.
was taught. Something
Not
similar. I
taught.
think it's called something else. I'm sure.
Okay, anyway, no problem. So now you
And
can
sir,
easily,
while we're at it, just if you can quickly go back to the comment that you made in that example 3 about the Nyquist plot, about the
yeah,
symmetricity. You
yeah,
said that when the plot is symmetric with respect to x and y
yeah,
axis,
yes,
there is no term like positive or negative phase margin.
Mhm.
So I don't get it. Like if it
So
is Nyquist plot is symmetric with respect to, it is symmetric with respect to x-axis, right? I think it is always symmetric, right? The
yeah,
x-axis at least.
yeah.
And now you're saying that if it is also symmetric with respect to y-axis, there is no concept of positive or negative phase margin. How exactly? Like I don't get it.
So here, for this example, phase margin, you can say this angle or this angle. So this angle, if you take, it will be positive phase margin, and this angle, sorry, this angle if you take, it will be positive phase margin, and this angle if you take, is negative phase margin. Since this is symmetric about your x-axis, so positive phase margin equal to negative phase margin here.
Okay, so you basically need symmetricity about x-axis, right? Not about y-axis. It is not required, right?
Not about y-axis required. Okay.
Okay.
So, well, at the end we can take some questions. So this is your, so you can derive that. Now one can show that S alpha t equal to 1 by 1 plus gc into S alpha g. So that is, I am not deriving here. Try. It is very simple. Try simple. It is very simple. Okay, so I am not deriving. So this is, so what is the, so now the relation that what I wanted to say is the closed loop sensitivity equal to 1 by 1 plus gc into open loop sensitivity. So as you know from your basic electronics class also, I think hopefully, that as feedback reduces the sensitivity of the loop, sensitivity of parameter variation against loop. In your analog electronics class also, I think you might have seen you might have studied this kind of relation. So that is, so now I will term this S alpha T equal to capital S into S alpha of G. So this S I will term as sensitivity function. This S is known as, so S, this is very important thing in robust control or in advanced control, anything. So this is equal is, so this is very important. This is what? Sensitivity function. This is function, not sensitivity. It was sensitive function. So from this relation, you can easily see. So that means S also you can write like this: S equal to 1 divided by 1 plus L. What is L? L equal to loop transfer function. This is equal to G into C. So to reduce sensitivity, what you should have to reduce sensitivity, L should be as much high as possible. So to reduce S, to reduce S, L should be as much high as possible. But there are some other limitations that I will slowly come. You cannot make arbitrarily high S, L, then noise will enter into the loop. So all those problems will occur. Okay, but there some trade-off has to be made. Okay, so now I want to say you what is S, what is physically. So now we have studied Nyquist plot. So here S means what with respect to Nyquist plot. So that I will try to say. So what is S now? S j omega. S j omega equal to 1 by 1 plus L j omega. So this implies S j omega mod, if you say, take inverse equal to mod of 1 plus L j omega. Okay. So now what is 1 plus L j omega? Can you say? 1 plus L j omega is what? So if you draw a typical Nyquist plot, omega equal to 0, omega equal to infinity. Okay. So this is your -1 point. So what is 1 plus L j omega? Suppose if you take this point, say omega equal to omega 1. Suppose omega 1. What is L 1 plus L j omega? So this will give you 1 plus L j omega, this distance. Okay, I should use different colors. So this distance will give you, because this is 1 and this is L j omega, so this will give you, 1 plus L j omega. This is actually 1 plus, that means S j omega inverse is distance of the Nyquist plot from -1 plus J0 point at frequency omega. So now, if So if so as you know, -1 point is a critical point. So for stability of the system, Nyquist plot, if any parameter variations or any unmodeled dynamics is there, so because of that, what may happen? Nyquist plot may touch. You are verifying that okay, my nominal is not touching -1 point, but because of some parameter variation or something, the Nyquist plot corresponding to the part of loop transfer function may touch -1 point. So for robust stability, the Nyquist plot of the loop transfer function, even nominal loop transfer function, should be as much far away as possible. So for robust stability, the Nyquist plot should be as much far away as possible. So now, so then what you have to find? So what we are interested in? So we are interested that what is the minimum distance given a Nyquist, given a loop transfer function? What is the minimum distance of the loop transfer function from -1 point? So the minimum distance means, so S infinity Sj omega inverse is the distance simply at frequency omega. So what is the minimum distance? So minimum distance means minimum. So minimum distance. So now let define. So this definition is very important. Ms equal to max of omega mod Sj omega. This implies Ms. So this Ms implies what? Then the peak value of mod Sj omega, peak value of Bode plot of Sj omega. Bode plot of sensitivity function. So that is also known as infinity norm of sensitivity function. This is also known as, Ms is also known as infinity norm. That is the definition of infinity norm. Infinity norm of S. So Ms inverse equal to what you can write? 1 by max. So this means Ms inverse equal to, you can write mean of omega of mod of 1 plus Lj omega. So now you see, so this implies Ms inverse is the minimum distance of the Nyquist plot Lj omega from -1 point. So that means what is now Ms inverse? If you saw in this, again I'm that figure I am drawing for convenience. This is a real of Lj omega. This is your imaginary of Lj omega. So suppose this is your -1 point. So how to get it? You will draw a circle such that circle of maximum radius, such that that circle will just touch the Nyquist plot. Okay, so I am trying to draw that circle. So although my drawing is proper. So this is your, so what is then MS inverse? MS inverse is this radius. This radius is MS inverse. Okay, so that means just, so this is also known as S, that means a sensitivity circle, you can say. I am naming it as sensitivity circle. Okay, so this is omega equal to 0, omega equal to infinity. So that means, as you can easily see, that if your Nyquist plot is far away from -1 point, that means MS inverse is as high as possible. That is good. That means even if some parameter variations or perturbations occurs, then as the Nyquist plot Nyquist plot lies away, much away from -1 point, so it will not touch -1 point, even if some parameter variations are there. So that means MS inverse. So also, so this implies MS should be, MS inverse should be as high as possible, as large as possible. That means MS should be as small as possible for robust stability. So this is a very important information as far as robustness, loop robustness is concerned. Okay, so now the question is whether you can make MS always small, or there are some limit. Is it possible to make MS small always? That we'll try to that we'll just try to visualize. So now, so S equal to what? 1 by 1 plus L. So as L LS is LS has, as LS has low pass behavior. Because why LS has low pass behavior? Because most of the physical plants are strictly proper in nature. So LS and controller is biproper or bicasual. So that's why LS is always strictly proper transfer function. So that's why LS has low pass behavior. So this means LS Lj omega much less than 1 at high frequency. So this means Sj omega. So Sj omega you cannot make arbitrarily small. So it is approximately 1 at high frequency. So that is unavoidable. So Lj omega you cannot make arbitrarily small. So so the only thing is, so high frequency at Sj omega equal to 1 at high frequency anyway, that you cannot avoid. So this, so for robust stability, at least Sj omega should be made small at low frequency. Okay, so that we can make. But so one important point, for unstable and non-minimum phase plant, S infinity you cannot, S infinity, there is always peak, there is always in mod S j omega plot. So that you cannot avoid. So for example, for say for example, that ms will be greater than equal to mod of z plus p divided by z minus p, where z and p are unstable pole and zero locations of a plant, where z comma p are unstable, zero and pole location of a plant. Non-minimum phase unstable plant. So that is of course greater than equal to 1. So ms even less than 1 you cannot guarantee for unstable non-minimum phase plant. For unstable non-minimum phase plant there will always a peak in S j omega plot, and therefore ms will be greater than 1. So this implies unstable NMP plant suffers from poor robustness. This means difficult to control. So unstable non-minimum phase plants are difficult to control because of this reason. Okay. So now the just one example we will just consider, that as I said that gain margin, phase margin are not enough. So one such a case I will say that where gain margin, phase margin are good, but the system has very poor robustness, and that is because their ms is high. Okay, so that one just simple example I will tell you, one example of a flexible structure. So an example where gm pm are good, but ms is high, implying poor robustness. Okay, so that example just I will tell you. So this is the system. LS. Just LS means here controller I have incorporated inside. Suppose this is your LS. LS is this one, 0.38. You can verify using MATLAB also. 0.1 S plus 0.55 divided by S into S plus 1 into S square plus 0.06 S plus 0.5. Okay, so if you draw Nike's plot for this plant, for this LS, then it will look like this. Imaginary of L omega. The Nike's plot shows this is your minus 1 point. This is your minus 1 point. So it will be like this. Omega equal to 0, omega equal to infinity. So here, if you draw a unit circle, my drawing is not good. This is suppose unit circle. So you can verify that. So here this is your phase margin, this is your phi. So phi will be almost phase margin equal to 70 degree, and here you can easily see what is the gain margin. Upper side gain margin, upper side gain margin is infinity. There is even lower side gain margin, upper side gain margin are both are lower side gain margin is infinity, and lower side gain margin is arbitrarily small and upper side gain margin is infinity. So gain margin, just I am writing here infinity, means upper side say. And lower side gain margin also you can make arbitrarily small. From the figure is also clear. So but if you just check what is your MS, that is sensitivity, MS is 3.67. That means MS inverse equal to 0.2725. In fact, you can draw a circle like that and then you can verify. So this circle, so this is your sensitivity circle, S circle. You can see this sensitivity circle radius, even I have not drawn properly. So sensitivity circle radius is very small. So that's why it is. So little bit parameter variation, if little bit parameter variation is there, then what will happen? This point will touch -1 point. So system will start oscillating. So this is so there. So this example I have given just to show that gain margin, phase margin specifications are not enough. We have to have low MS. That means the S circle radius should be as high as possible. Otherwise, your design, your classical design may suffer from robustness. Okay. So this is actually an example of flexible dynamics. So these are flexible modes. So if suppose a flexible spacecraft, flexible structure because of solar panel and all these things. So this kind of flexible modes will offer. You can see a very low damping is there. This flexible structure. This is a system of flexible structure system. Example of, this is an example of flexible structure. Okay, so now the next thing is that naturally question arises, okay sir, gain margin, phase margin, so how to guarantee this? So okay, suppose I have got a sensitivity norm low, then those who are classical engineers, those still believes on classical margins. They will say, okay, your gain margin phase, your sensitivity norm is sensitivity circle is sensitivity circle radius is large, but how to guarantee that gain margin, phase margin is good? So that means low MS. So we have to have some relation between MS, phase margin, gain margin. So we should have some relation which will guarantee that if MS is less than equal to say 2, then we can always guarantee gain margin greater than 2, phase margin greater than 30 degree kind of thing. So what is that relation? So the relation between gain margin, phase margin and sensitivity, that relation is also important. So relation among GM, PM and MS. Since MS means sensitivity peak. Okay. So this relation is there. This relation you can easily prove. The relation is this one. MS. Your gain margin is this relation is there. Gain margin is greater than equal to, here gain margin I have considered, remember that upper side gain margin, so that's why I am writing here max. Gain margin max is ms divided by ms minus 1, and phase margin I need not to include max mean. Phase margin is greater than equal to 2 into sine inverse 1 by 2 into ms. So gm max, so gm max, sorry, gm max means upper side gm. Similarly, lower side gm relation is also existing, that I will give you as home task, so that I will give. So this is ms minus 1. So now this you can always prove for a typical Nyquist plot. Just before proving that this is the relation, so just I want to say, suppose, now the question is, suppose we want gm max greater than 2 or greater than 6 dB, and phase margin greater than equal to 2, and phase margin greater than 30 degree. So what should be ms? That is the question. Because as you know, for a practical design, gain margin should be greater than 6 dB, and phase margin should lie between 30 degree and 60 degree for a well design. So gain margin, in fact gain margin should be plus minus 6 dB, so that you can increase the gain by loop gain by double, or you can make it half also, plus minus 6 dB, that's why. And phase margin it should be in between 30 degree to 60 degree. Why? Because phase margin is closely related to damping ratio. So damping ratio equal to phase margin divided by 100. So phase margin 30 degree approximately. Phase margin 30 degree to 60 degree means your damping ratio is almost 0.3 to 0.6 kind of thing. So which is a reasonable value for a well designed system. So now for this example, for this question, so you can easily see that what I want, gain to guarantee, so solution to guarantee gm max greater than equal to 2, what it should what I should satisfy, one can guarantee. So ms by ms minus 1 greater than equal to 2. So this will give you ms should be greater than equal to 2 ms minus 2. So this implies ms should be less than equal to 2. Now this is ms less than equal to 2. Now for the other one, that means 2 into sine, now to guarantee phase margin greater than equal to 30 degree, what I should have, 2 sine inverse 1 by 2 ms should be greater than equal to 30 degree. So if you do this inequality, if you solve this, then ultimately you will get, please check it, you will get ms should be less than equal to 1.93. Please check it. I am not checking this one. I have already checked. I am not deriving this one again. Then sine inverse 1 by 2 ms would be 15 degree. Then 1 by 2 ms would be greater than equal to sine 15 degree. From there you will get it. So then ultimately, so to guarantee both both GM max greater than equal to 2 and PM greater than equal to 30 degree, where MS should be less than equal to the lowest one you should take 1.93. So this is the answer. Okay, so that means for a good design, your sensitivity norm, that infinity norm of sensitivity function or MS should be less than equal to 2 or less than equal to 6 degree, which will guarantee your gain margin greater than 2, phase margin greater than 30 degree. Even if you make it small, then your gain margin will increase, phase margin will increase. So from this example or from the above relation, then it is clear that smaller value of sensitivity function, smaller value of MS will also guarantee desired gain margin, phase margin. So this is your conclusion. Smaller value of smaller value bracket at least less than 2 guarantee good smaller value of MS guarantees good GMPM. GM max I should write PM. Upper side gain margin. Similarly, lower side gain margin also one relation is there. So also I have to prove this one, and that you can easily prove just I think first I will take any question if it is there. Is there any question? Hello? Is there any question?
Sir, like I would, yeah, sir, like, uh, could you say like in the system diagram which you had drawn below with LS, like, so why are we not considering any input or output in this discussion or
Because the
analysis?
robustness input output are non-linear. This is a linear system. Okay,
Okay,
linear
so
time
only
variant
the
system.
system matters.
Yeah. Only the loop transfer function is enough. We need
Oh,
not to consider any input output for robustness study. Okay.
okay, sir.
For Nyquist plot, for gain margin, for drawing root locus, do you need any reference input output? You do not, right? So Nyquist plot, root locus, all these things you will to draw that one only you need GS into CS or loop transfer function. But you will break the loop and you will obtain loop transfer function. Got it?
Yes, sir.
So any other question? Okay, so just 2 minutes more I will take just to prove this one, because this can be proved in a very simple way. Just proof. Okay, just 2-3 minutes more I need. Then this portion I will finish. So this is your real of LS. Suppose this is your real of LJ omega. Just wait. And this is your imaginary of LJ omega. So this is your omega equal to 0. This is omega equal to infinity. And this is your minus 1 point. And this is your unit circle. So here just proof using a typical Nyquist plot, that I should write. Proof using a typical Nyquist plot, end plot. I have just written. So here, what is your GM max? So this distance will be 1 by GM max. This distance, right? So this is 1 by GM max, and what is your phase margin? So this is your phase cost of frequency, and this is your gain cost of frequency. Those things I am not writing. So this is your phi. This is your phi phase margin. So phi is your phase margin. Phi is your phase margin. Okay. So now what is your so I will draw that unit circle, sensitivity circle. Sensitivity circle, if you draw, so it will be like this. So this is your sensitivity circle, S circle, and this radius is what? This radius is your MS inverse. Okay. So now from the figure it is clear that what is your 1 by GM. Just wait. So from the figure, if you just mark it like this, this is O, suppose this is your A point, this point is suppose B, and this point C. Okay, and I am also drawing, suppose this is a triangle. Okay, and I am also dividing it. Okay, obviously this point is D, suppose this point is D. So from the figure, what is OA? This is this is B, AB. Okay. So what is your OA? OA is greater than OA is of course greater than MS inverse. This implies 1 minus OA is what? OA is 1 by 1 minus 1 by GM max greater than MS inverse. So this from here you will get GM max is greater than equal to MS divided by MS minus 1. Okay, and from the triangle, OBC, from the triangle OBC, OC is greater than equal to your MS inverse. So this implies OC by 2 is greater than equal to 1 by 2 MS, and from there you can see OD is greater than equal to 1 by 2 MS. What is your OD? From the figure, your OD is your sine of 5 by 2. You can easily see, because this is a triangle where this two sides are equal, unit radius. This equal to angle of OBD will be sine of will be equal to 5 by 2. So OD is will be equal to just sine of 5 by 2. This is equal to 1 by 2 ms. So this implies phase margin is greater than equal to 2 sine inverse 1 by 2 ms. So here, just for your information, you just write, better to mention ODB in triangle OBC, OB equal to OC, OB equal to OC equal to 1. Okay. So then your sine of 5 by 2, that means this angle will be 5 by 2. So 5 by 2 will be OD by sine of 5 by 2 will be what? OD divided by OB. So OD by OB, since OB equal to 1, so OD will be equal to then sine of 5 by 2. That's why I have written this one. Okay. So okay, this much is for today, and possibly from the next class I will see today's video. Okay, and then if there is some lag, I also noticed that in the last class there is some lag between my voice and the things what I am writing. So if there is huge lag, then I will take I'll just upload my recorded class. Okay, and in the meantime also sometime I'll take some live class to clear your doubts. Okay, I'll see today's lecture. If there is considerable lag, then I have to go like. Okay, thank you very much.
Sir,
Yes.
these relations are for a general Nyquist plot. Like for example, the one in which our MS was high, but the GM and phase margin were good. So that was not a typical Nyquist plot. So these relations which you told are for just general typical Nyquist plots.
Yeah. That relation I have done for an Nyquist plot, but general derivations are also there for convenience. I have done it for a typical Nyquist plot. Okay, but then generally you can also prove. In robust control class, those things are proved in general.
So sir,
Okay.
these relations are always applicable.
Yeah. These relations always hold.
Okay, sir.
These relations always hold. Okay.
Yes, sir. Thank you, sir.
Thank you.